Moving on to next slide would be a brief on designing isolated foundations. All right. So step one, I have listed out certain steps which might help one aspirant to, design and come out with a size of foundation and rebar required to comply with his engineering requirements and put it on the drawing. So this entire steps involve Indian standards, IS 456 and IS 1893. So step one suggests calculation of loads in accordance with combinations defined in table 18 of the code. All right. So that is the snapshot of table 18. And it says dead load and imposed load, dead load with wind load, and dead load imposed load with wind load. And the other required combinations also is stated in IS 1893 Part 1, suggests when lateral load resisting systems are not aligned with mutually orthogonal direction, additional 30% contribution of other horizontal earthquake load shall be considered, which means that once we're considering earthquake contribution into the load combinations, 30% of one directional, other directional earthquake load contribution needs to be considered into the orthogonally other direction for our combination. All right. So in this snapshot, you could see that there isn't any earthquake mentioned anywhere, but the code suggests that for earthquake as well, the WL, which is wind load, can be replaced and should be replaced with EQ as earthquake. All right, coming up to a step 2, which suggests understanding the foundation and the bearing conditions by studying the geotechnical report and suggestions along with bore log details. All right, so as I explained a little earlier, that geotechnical report will suggest us what is the bearing capacity of soil that we are considering for such foundations. All right. And what would be a suggested depth of foundation for the plant or the location or a specific bore log location for that matter. Once that is decided, depth of footing and bearing capacity of that location, one can proceed on to the next thing, which is basically understanding what is the load that is coming on top of the foundation and the bearing area requirement. Although one thing what one might have to note is that the groundwater table depth, that is a critical point which would be provided in a geotechnical report, which one need to take in account for reduction of soil density if the water table is such that it during the rainy season it floods, or during the dry season it is not as deep as the depth of the foundation. Step 3 includes a initial iteration size, which can be considered by checking with the allowable net bearing capacity of soil, where the maximum load of the foundation that need to bear. All right. So one has to rely on initial judgment of the load, and it is very simple. The total load that is exerted once you've made all your load calculations and combinations, you would have 3 different type of loads. One is a vertically downward, which is called a P force over here by the slice side, and the other 2 different forces would be shear forces along the plane of the footing slab and the moments that is generated at the base of the raft. So by the virtue of a thumb rule, total vertical force divided by a cross-sectional area of the foundation would give you a bearing which needs to be compared with the foundation bearing capacity of that particular depth. Step 4 includes a serviceability check with the service load combinations. Going back to the previous slide, you could see that the table 18 suggests 2 different types of combinations, one with a limit state of serviceability and one with limit state of collapse. So we in our engineering stream, we would call this as serviceability combinations, which would generate by the virtue of combining all the initial load cases, and this would be termed as strength combination because it's in a limit state of collapse. Similarly, the service combinations need to be considered for the serviceability checks. And what do we need to check initially for serviceability? Say the first thing which one might need to check is the check for bearing pressure with respect to gross and net. The entirety of the load, along with its surcharge and the moment and the total vertical force, that has to be bared by the bearing straight of the soil. This gross and difference between gross and net, I will come during the explanation of my next slide. And also, checks need to be made for submerged and saturated conditions of soil. As I mentioned earlier, that the groundwater table needs to be considered during an engineering process, because during a rainy season, soil may be submerged and the entire thing gets flooded. Then you have to check for a submerged condition. Otherwise, the soil will be saturated under normal conditions. And other serviceability checks include, check for uplift in the foundation and check for overturning and sliding of the footing. Step 5 includes the strength check with strength combinations. One need to calculate the bending moment and the rebar requirement according to IS 456 and SP 16. And then the shear force calculation for the depth of slab requirement as well. And the final check one needs to perform is the crack check, which is also comes under serviceability combinations with a service moment that needs to be checked for the nearest rebar at the nearest tension zone. So we will now want to go through a case study, and I will open a PDF. So this is one of my previous worksheets, which I have developed over the years, and it helped me design plenty of footings and isolated foundations, and it's pretty straightforward as well, and easy for me to explain too. So basic design parameters that I had considered earlier are greater concrete, greater rebar, clear distance for main reinforcement, net allowable bearing capacity. Now, why do I call it a net allowable bearing capacity? Because if you look at the diagram right side where axes are mentioned, you can see there is a level called FGL, which is finished ground level, and there's a level called bottom of foundation, which is BOF. So 5 meters are the difference. And if you take out the entirety of the soil and excavate that 5 meters, then the bearing capacity of the soil tested at that level would give you a net allowable bearing capacity. Consider this, that you have removed the mass of the soil, 5 meter mass of the soil from that area. Then the bearing capacity is that. But then what is the gross bearing capacity? We will come to that later when we use that gross bearing capacity. Is that the entirety of the mass of the soil which was already there, the bearing strata was also bearing that mass as well. So the gross bearing capacity of that particular strata is the net allowable bearing capacity plus the addition of the mass, 5 meter soil mass. All right, that is the basic difference between net and allowable, net and gross, basically. And then you have the density of concrete, density of soil, overburden pressure. Wherever applicable, overburden pressure is somewhat on top of the FGL, which is not exactly working on top of the foundation directly, but it is getting transferred through the soil. Now coming down to the dimensions, where previously I've used certain dimensions. 550 by 750 on the column size, footing size is 2.5 meters with a 0.5 meter of thickness. And depth of soil above is basically nothing but depth of soil, which is excavated soil minus the depth of foundation. And height of pedestal would also be the similar. Area footing is multiplication of Lx and Ly, which is planned dimensions of the footing on either axis. And section modulus is nothing but bt square by 6. It's a formula, which is basically b times L square by 6, which is b. If you consider on the x-axis, b is x dimension and L is y dimension, and vice versa on the other direction. So this particular example is basically from a steel structure reaction. All right, a steel structure is generally designed for pinned jointed connections, and a pin jointed connection with yield with vertical load and two-directional shear forces. All right, so the design forces and moment from analysis file, as it says, has number of load combinations, and then you can see that there is no moment here because the entire force is getting exerted right here. Okay, and then this force needs to get calculated, and I need to calculate a force around this point for which to design the foundation. All right, so these are my serviceability combinations, which are my 2000 load combinations and vertical loads and shear. Okay, scrolling down, there are plenty of combinations, so these pages are really not nothing to explain over here. And then the next table which starts is basically ultimate load combinations, which I also need to have in order to design for bending moment and shear. All right, now coming down to a basic load calculation, which is a basic of calculating the self-weight of the footing, which is, you can see it's pretty self-explanatory. We have calculated the weight of the soil, which is basically the area of the foundation minus the area of the column and the depth of the soil with the specific gravity of the soil. With weight of the surcharge, we did have considered 10 kilonewtons, that's 1 tons per square meter of surcharge load due to vehicular movement over here. And then there are some weight calculations for additional loads, which in this case are none, and weight of submerged soil. Now, again, as I mentioned earlier, that the groundwater table level is very critical in designing the foundations. So you can see that when I calculate the weight of the soil, it takes 18 as soil specific gravity, but when I consider submerged soil, 18 is now made as 8 because self-specific gravity of water is 10, and we need to subtract that in order to consider the load of submerged soil. All right, so check for bearing capacity is the next check that we perform in our calc sheet. Factor for increasing SBC. This factor is provided in IS 1893 for inclusion of horizontal forces effects in foundation design, and the code suggests that 20%, 25% can be increased while including earthquake or wind load. And as I said previously, that the bearing capacity that I had considered in my design considerations was a net bearing capacity, and now this is calculated as a gross bearing capacity. All right, so this amount of soil that is included for the gross and allowable safe bearing capacity for lateral load cases gets multiplied with the factor increasing for SBC. Now comes the calculation for saturated conditions of pressure calculation. I'll scroll up to my initial diagram and tell you that the pressure is calculated at 4 points for a rectangular or square foundations. And the pressure calculation formula is pretty simple. P by A, that is P is the vertical load by the area of the base, plus minus M by Z. Z is nothing but a section modulus. And the same thing is done over here with the formula, and four corner pressures are checked for the loads and the moment that is generated from the shear force below the bottom of base plate, and the maximum and minimum pressures are checked with respect to liable bearing capacity for static loads and lateral loads. And that too is done for a saturated conditions. Scrolling down, I have made another calculation for submerged condition where the soil weight reduces. And then another table which calls up for calculation for bending moment and shear force. So from the pressure, one needs to calculate a bending moment. So for that, for us to understand how it has been calculated, one needs to see this diagram, which is basically a section cut along x-axis. And if one has to consider that P1, P2, P3, P4 are four corner pressures, then we need to average it out at the center to design this raft. So the averages are made in accordance with that. P1 plus okay, this section is vertically cut, this section is horizontally cut. So you can see that P1 plus P2 is average for this end, and P3 plus P4 is average for this end. And this becomes basically a slab with varying load, and bending moment and shear force calculations from that is pretty easy, right? We have arrived for the bending moment and shear force calcs with our strength load combinations, and have considered the maximum for designing the moment and a rebar. One needs to check for a limiting moment, from that a minimum depth requirement, and check for what is the effective depth that one has considered for the iteration and whether it is safe or not. And then one needs to calculate MEV/BD square factor, from which you can either put into the formula or look back into SP16 charts for arriving percentage of steel required, and from that you can derive at this steel requirement. And the shear force as well, accordingly, what we've calculated and take out the maximum shear force, and simple view by BD can be done to check the shear stress, or you can calculate the nominal shear stress VC for the concrete and the steel provided. The beta value calculated, you could find the equation mentioned in SP16, and in turn calculate the tau C value and come up with a nominal shear strength for the percentage of rebar provided. And as usual, VC needs to be higher than VU in order for your shear sufficiently transferred into the foundation, the soil. Same calculation happens on the Y direction, and moving on to a check for two-way shear. But before we go for a two-way shear, I would want to point out a particular item which comes for a one-way shear, is that the shear value is calculated D distance. D is basically effective depth away from the face of the column. So once again, we will go to the top and see that this is the pedestal or the column from which one has to consider a distance D, say some here. From there, the pressure value has to be calculated, and then the shear value needs to be considered, because the code suggests that the shear plane occurs. So from the distance of the face of the support, in this case support for the slab on the other direction, and the shear plane happens to have a crack length like this, crack progression like this. So we need to consider a shear plane which is coming from the D distance of the face of the column, and check for the shear capacity of the slab at this particular position. So one-way shear check is performed. One needs to go through the two-way shear considerations. Similar concept, and the only change is that instead of D distance, the code suggests that it needs to be considered at D by 2 from the face of the column, and a punching perimeter has to be arrived from this d/2 area, and accordingly allowable shear and actual shear stress needs to be cross-checked. And the final checks for an isolated foundation, the check for overturning and check for sliding. So what is an overturning moment? Again, as mentioned in my earlier slides, that an overturning moment or the overturning and the sliding checks has to be performed during the serviceability, because the foundation has to give its meet the serviceability criteria as defined in the code. So the total overturning moment is nothing but the moment that is generated at the base of the raft. All right, be it's a moment from the force exerted by the concrete column, or be it the horizontal force that is exerted at the top of the concrete column and then that creates the moment at the base of the raft. It's a pretty basic calculation with horizontal moment, and that needs to get counteracted by the vertical load that is coming on top of the foundation. What are the vertical loads? We have a vertical load on top of the column, we have soil load, we have surcharge, and the concrete self-weight. That's the only thing that resists the moment. So we calculate the resisting moment due to soil, above footing, and foundation weight by multiplying the entire load that is generated, soil, foundation, self-weight, and the vertical load, and multiplying it with half of the breadth. So it gives us a resisting moment at the base of the foundation. And that check is performed on submerged and saturated conditions. And for sliding check, similar concept, but without the moment, we consider here only the horizontal forces which actually can get exerted at the base of the raft of the foundation, and then induces the foundation to slide. So as per the geotechnical report, one can find out the coefficient of sliding between soil and concrete, and accordingly check what is the exerted force, horizontal force on the foundation, and the total foundation load, the foundation and the soil and the pedestal and the tie beam, whatever, the total load multiplied with the coefficient of sliding between concrete and soil, and then calculate the factor for sliding. So these are two pretty simple checks on sliding and overturning, and which concludes the design of a foundation with the initial sizes of the iteration. All right. You can see that the bottom reinforcements are provided as such, but I haven't discussed anything about the top reinforcement provided, because top reinforcement comes up for a certain condition where the plate wants to bend on the other direction. All these things are happening because the force is vertically downward. We can see the force is vertically downward. The entire thing bends. The plate bends like so. The plate tries to bend like this, but when the force is reversed, when the force is reversed and we have an uplift, the bending becomes reverse due to the weight of whatever is here, and here. Whatever is here. So what do we have here? We have soil, we have submerged condition water, and we have some surcharge. For that, the plate bends on the other direction. And for that bending moment, one needs to provide a rebar on the top of the foundation as well. Otherwise, there isn't much requirement of providing the top rebar, but one can provide the top reinforcement for general crack width requirement as well. And that concludes the explanation of the case study.